This is a video about the importance of droplet size in gas scrubbing systems. Our nozzles are commonly used in gas scrubbers of various types, and they're a critical component, and drop size is a key factor in achieving optimal gas scrubbing systems. So in gas scrubbing systems, what we're looking to do is interact a gas flow with a liquid spray of some description. The spray will then either absorb contaminants and knock them out of the gas flow, or will induce some kind of chemical reaction to again remove the contaminants. A good example of the latter would be flue gas desulfurization or ammonia sprays to remove nitrogen oxides. Now, in order to absorb or react with the gas, we need to ensure that a big surface area of liquid is in contact with the gas, as big a surface area as possible. The larger the surface area, the more reaction or absorption will occur, so the more efficient the gas scrubber will be. Now, drop size is what dictates the overall surface area of the spray. The smaller the drop size, the bigger the overall surface area of the spray will be. So if you imagine a litre of water atomized to, say, 400 microns, this would have half the surface area of the same litre of water if we were atomizing it to 200 microns, and only a quarter of the surface area if we were to further break that apart into 100 micron drop sizes. So each time we halve the drop size, we double the surface area available, and so we're doubling the potential for reactions or absorption in the gas scrubber to occur. Now, it might be tempting, therefore, to assume that for any gas scrubbing system, we just want to get the drop size as small as possible. This would maximize the surface area of the spray and so improve absorption or reaction. But there's quite a lot more to consider than this. Finely atomized sprays do indeed produce much greater surface areas, but the light drops also get rapidly entrained in gas flows. This means they're not able to reach the outer parts of a fast-moving gas flow, and so parts of the gas will not come into contact with any of the reagents at all. So we're going to miss parts of the gas. Now, obviously this won't do. Now, one could compensate for this by having a large array, perhaps of tightly packed nozzles over the entire gas flow so that it's all treated. But this is where a theoretically good idea comes up against practical reality. How are we going to get those nozzles out for maintenance in such an array? What about the cost of the extra pipe work, etc., etc.? So there needs to be a balance between getting the small drop sizes that theoretically will produce greater absorption and having a big enough drop size to penetrate the gas flows with a reasonable number of spray nozzles so we can get proper coverage of the whole flow. Now, another limitation on fine drop size is entrainment within the scrubber. If a lot of the liquid is being whipped up into the gas flow, this might overload mist eliminators further up the gas stream, and therefore they may escape. Now, there's not a lot of point in absorbing contaminants only to have them escape the scrubber due to entrainment and overloaded mist eliminators. So again, we need a balance here between smaller and larger drop sizes. So what does this mean for nozzle selection? Well, it's impossible to give specific advice in this short video, but as a general rule is to speak to a nozzle supplier that understands all of this. When looking at scrubber design, we need to consider not only the overall surface area of the spray, but also its larger and finer drop sizes and how that spray is constituted. All sprays consist of a spectrum of different drop sizes. There's not just one uniform drop size in any spray. And three drop sizes are actually of importance in scrubber design. Firstly, the source amine drop size. This is the D32. This is a really good measure of the relative surface area of any spray. So clearly very important in scrubber design. So we need to know this so we can compare different sprays' ability to absorb or react with contaminants. But another drop size that's important is the DVO9. Now, this is the drop size which 90% of the volume of the spray is made up of drops smaller than this drop size. So this is a measure of the heavier drops. The heavier drops kind of dictate where the spray will go. These are the ones that will penetrate further into a fast-moving gas flow. This is the drop size we need to understand to work out where the spray is going to actually end up. Those bigger droplets also serve to actually carry smaller droplets further into the spray as well. So understanding what the DVO9 is and the D32 is very important when considering overall scrubber design. Finally, the DVO1 is the drop size such that only 10% of the volume of the spray is made up of droplets smaller than this drop size. So this is the measure of what we call the fine droplets within that spray. Knowing what this is and how these drops will behave in a gas flow can help us look at and estimate things like the amount of fluid that's going to get entrained with the gas flow, and so we can calculate mist eliminator load and things like that. As I mentioned, it's impossible to give firm advice on any specific gas scrubbing application in a video of this nature, but what we are giving advice on here is to talk to a nozzle supplier that understands all of these different drop sizes, their importance, and how they relate to overall scrubber designs. We supply nozzles to gas scrubbers all over the world, to engineering companies large and small, to chemical companies large and small. This is bread and butter business for us, and so we can enter into a discussion about all these different types of drop size and which one's going to have the most implications for your scrubber design. So you're in safe hands with spray nozzle people when it comes to specifying nozzles for gas scrubbers of all types.